On June 14th, I witnessed an extraordinary moment in space exploration history while assisting my friend, everyday astronaut, in filming SpaceX's third integrated flight test of Starship. This test marked a monumental achievement as Starship reached space for the first time, successfully igniting all 33 of its Metalox Raptor engines. The launch also featured a significant improvement over the previous test, a successful hot staging separation. During this maneuver, the Super Heavy booster powered down all but 3 of its engines, while the 6 second stage engines ignited before separation. This was a stark contrast to the prior test, where the booster exploded, and a fire from a planned oxygen dump prevented Starship from reaching space. This time, the second stage soared past the Kármán line, achieving a maximum altitude of 234 kilometers, just shy of the International Space Station's orbit. SpaceX could have performed a boost burn to reach orbit, but opted for a suborbital trajectory due to unresolved issues, including an uncontrolled roll that prevented a reentry burn. This decision ensured Starship didn't become the largest piece of space debris in history. Its Raptor engines, the first full-flow staged combustion cycle engines to fly, enable it to carry up to 150 tons to low Earth orbit. During re-entry, Starship provided breathtaking high-definition footage of a plasma cloud, a phenomenon caused by hypersonic speeds. Unlike the space shuttle, for which no public re-entry footage exists, I know because I searched for it while working on a space shuttle documentary. With new rocket companies emerging often likened to middle-aged men buying sports cars after a divorce, Starship stands out. Its capacity to carry massive payloads opens new possibilities. Unlike any rocket before it, Starship is designed to be fully reusable, with both the Super Heavy booster and the second stage intended to land back on Earth for refurbishment and reuse. SpaceX envisions Starship as the primary transport for Earth orbit, the Moon and Mars. However, some speculate its true purpose is to launch more Starlink satellites, which dominate the space industry's revenue. The choice of methane as a fuel supports SpaceX's long-term ambitions. Methane offers a middle ground between kerosene and hydrogen, providing better performance than the former and easier storage than the latter. Its real advantage lies in reusability and interplanetary missions. On Mars, methane can be synthesized using the Sabatier process, combining carbon dioxide from the Martian atmosphere with hydrogen over a nickel catalyst under high temperatures and pressures. Carbon dioxide, with the highest freezing point in Mars' atmosphere, can be extracted by cooling the air, condensing it into a liquid. Hydrogen, however, requires water deposits to be mined, posing a challenge for long-term goals. For now, methane's immediate benefit is its compatibility with reusable rockets, reducing soot from unburned fuel that could clog engines. The Raptor engines are a breakthrough, being the first liquid rocket engines to use a full-flow staged combustion cycle in flight. Unlike the open-cycle F1 engines of the Apollo missions, which burned a portion of fuel and oxidizer to power turbines and expel the exhaust, Raptor engines are closed-cycle, wasting no fuel. Open-cycle engines burn fuel-rich mixtures to keep turbine temperatures low, but this produces soot, as seen in the dark exhaust of SpaceX's Merlin engines. Raptor engines run all fuel and oxidizer through pre-burners, with the fuel turbopump using a fuel-rich mixture and the oxygen turbopump using an oxygen-rich mixture. These combine in the combustion chamber for complete combustion. Methane's single carbon structure reduces soot formation, addressing one challenge. The oxygen-rich pre-burner, however, risks high combustion temperatures that could damage the turbopump. SpaceX mitigates this by passing all propellants through the turbopumps, lowering the temperature rise needed to drive the turbine. To combat oxidation, Raptor parts are cast in a heat and oxidation-resistant Inconel alloy, addressing issues seen in earlier tests where oxygen-rich combustion melted copper components, causing green flames and engine failure. Despite these advancements, challenges remain. The Super Heavy booster performed Starship's first landing burn during the third test, but exploded at 462 meters due to wind shear during its supersonic descent. The booster appeared stable until it relit its engines near an altocumulus cloud, where wind shear disrupted its flight. The grid fins struggled to stabilize it before the explosion. For the next test, SpaceX will likely focus on reducing velocity more effectively. Unlike Falcon rockets, the Super Heavy booster won't use landing legs. SpaceX plans to catch it with mechanical arms at the launch pad, eliminating heavy legs and protecting the pad from engine damage. This also allows faster turnaround times with refueling infrastructure nearby. The second stage faces its own hurdles. Its 6 Raptor engines, 3 optimized for vacuum with larger nozzles, successfully propelled it to space, but an uncontrolled roll prevented reignition for a reentry burn. Footage revealed the extent of the roll, which led to tumbling. Remarkably, Starship survived longer than expected, thanks to its thermal protection system of silica fiber tiles with fused silica glass coatings, similar to the space shuttles but likely with tweaks. Some tiles detached, possibly due to flexing of the underlying steel airframe. Unlike the space shuttle's aluminum structure, steel's higher operating temperature gave Starship an edge. The space shuttle used a no-mech string isolation pad to prevent tile detachment, a solution SpaceX may adopt. Starship's low ballistic coefficient, due to its large surface area and low weight, when empty allowed drag to slow it down effectively, unlike the space shuttle, which was designed for a 2,000-kilometer cross-range capability to meet Air Force requirements. Starship has no such constraints, simplifying its design. Hypersonic stability remains a complex issue, difficult to test without real-world data. SpaceX's footage from this test provides invaluable insights for future improvements. Once resolved, Starship could become the most capable launch system ever, with variants planned for crewed missions, cargo, lunar landings, and deep space exploration without heat shields or fins. A propellant depot variant could store hundreds of tons of fuel in orbit, requiring multiple launches to fill. The most immediate application, however, is launching larger Starlink satellites. Current Starlink satellites, constrained by Falcon 9's 5.2-meter fairing, weigh about 300 kilograms, with 60 fitting per launch. Starship's larger fairing allows for bigger satellites with stronger antennas, critical for Starlink's partnership with T-Mobile to provide rural cell coverage. Larger antennas will deliver stronger signals, overcoming the limitations of current satellites. Starship's fairing also enables massive space telescopes, unhindered by the size constraints that complicated the James Webb Space Telescope's design. SpaceX has applied for 9 launches with the FA, each bringing it closer to a fully reusable system. This third test was a significant step, proving Starship's ability to reach space and providing data to refine its design. The potential for scientific discovery, communication advancements, and interplanetary exploration is immense, but challenges like booster landings, second-stage stability, and tile durability must be addressed. Throughout this narrative, I've avoided focusing on Elon Musk, SpaceX's polarizing CEO. His contributions to technologies like electric vehicles align with progressive goals, yet his anti-regulation stance resonates with conservative audiences. This divisiveness obscures the full picture of SpaceX's achievements. To navigate today's polarized media, tools like Ground News, founded by a former NASA engineer, offer clarity. Ground News provides a data-driven, objective view of news coverage, showing political bias, factuality, and ownership for each story. For example, in a story about Texas approving a land swap with SpaceX, Ground News revealed that 60% of sources were centrist, 30% left-leaning, and 10% right-leaning. Left-leaning outlets highlighted the involvement of a state park, while right-leaning ones omitted it. By labeling sources' biases and ownership, Ground News empowers readers to contextualize information. I recommend their Vantage subscription, which offers a 30% discount through my link at ground.news/realengineering. This tool fosters critical thinking, essential in today's media landscape. SpaceX's Starship is poised to redefine space exploration, from enabling massive satellite constellations to paving the way for lunar and Martian missions. The third test was a milestone, but it's just the beginning. With each launch, SpaceX refines a system that could unlock a new era of space travel and discovery.